Hello and welcome to Textbook Engineering Problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition. We're working on problem number 2.33. The temperature in a process unit is controlled by passing cooling water at a measured rate through a jacket that encloses the unit. The exact relationship between the unit temperature, T in Celsius, and the cooling flow water flow rate, phi in liters per second, is extremely complex, and it is desired to derive a simple empirical formula to approximate this relationship over a limited range of flow rates and temperatures. Data are taken for T versus phi. Plots of T versus phi on rectangular and semi-log coordinates are distinctly curved, ruling out T equals T having a linear relationship with phi, and also ruling out an exponential relationship as possible empirical functions. But a log plot appears as follows. So if both of them are logged, then there's a linear relationship. A line drawn through the data goes through the points. So then they give us 2 points. Phi is 25, T is 210, phi is 40, T is 120. A, what is the empirical relationship between phi and T? Okay, so it's telling us that both of them are logged. So they're saying that this relationship, log T equals A log phi plus B. They're saying that that relationship is linear, and then it also gives us 2 points. Okay, so in this case, y equals mx plus b, y equals log t, x equals log phi, m equals a, and b equals b. Okay, so that's the equation of a line. We need to figure out what a and b equal with the 2 points that they gave to us. Okay, so the points that they gave to us, phi1 and t1 equals 25, 210, and phi 2 t2 equals 40 and 120. Okay, so if we're going to translate these into y1, y2, x1, and x2, then we need to take the log of 210, log of 120, log of 25, log of 40. Then we can calculate the slope equals y2 minus y1 over x2 minus x1, and b equals x2 y1 y2 x1 x2 minus x1. Okay, so we put these in our calculator and we get equals and the intercept. So that's it for part A. We have our equation defined, we have the slope and the intercept defined. So now we can move on to part B. Using your derived equation, estimate the cooling water flow rates needed to maintain the process unit temperature at 85, 175, and 298 degrees Celsius. Okay. So if T equals 85, 175, and 290 degrees C, what is phi equal to? Okay, so we can just use the equation, the relationship that we just got. So y equals mx plus b, when t equals 85, equals 53.4, t equals 175, v equals 29.14, and when t equals 290, v equals 19.06. And phi is in liters per second. And this is in Celsius. Okay. That's great. So that answers part B. Now we're on to part C. In which of the three estimates in part B would you have the most confidence in, and which would you have the least confidence? Explain your reasoning. Okay, so at low flow rates, small changes at low flow rates have large effect on temperature. So in these log situations, in this range, when you have the small flow rates, you're going to have really big changes in temperature. And so it's in this range that you're going to have the most uncertainty. How good were your parameters when you made these estimations? Log plots have this tendency to have these problems with them, especially if you only have two parameters or insufficient data in a certain range. Then you really aren't going to trust the estimates that are in the lower range, where a small change, you want to look for like this lever where I kind of imagine it as you have like a lever and a fulcrum, and this side has like a little tiny arm, and then this side has a really big arm. So if you change, this would be like phi, and then this would be temperature. You change the position of this lever up and down just a little bit on the phi side, and this temperature is going to swing, quite a bit, just because of where that fulcrum is placed. It's kind of like that. And so you got to be careful when you're using empirical correlations, especially in log plots, in that region. So that's the answer to part C. Great, thanks for joining me in this video. If you have any comments, let me know. If I made an error or something like that, let me know, and I'll try and address that in the comments. If there's any other problems from this book that you'd like me to check out, I can check out and do those, make a video on it, and help out. Otherwise, thanks for joining me, and I'll be happy to see you in the next video. Thanks. Bye.